is equal to n1 multiple n2. It can explain as the approximate product and the error term. The error term is s1 multiple s2. And the error term can be put in here and repeat again. It can repeat many times to get a more precise approximate result and smaller error. So if I repeat many times, the error will be reduced. And the approximate product will more closer to the real product, right? So this is the idea from the relative work. But it has some constraints. The first constraint is n1 and n2 must be the positive number. If one or both of the input is zero, it will result in high output error occur. So in the relative work, it has solved the problem is to suppose the two positive inputs and also detect the zero. If the error zero occurs, it will stop this operation and report the output is zero. So this is for the relative work. But we found that it cannot support one positive and one negative input. So we want to solve this problem. First, we have gathered output size signal from the first approximate multiplier and move to the size signal will be moved to the second and the third approximate multiplier. In our design, we use the 3 stages of the approximate multiplier because we found that if I use 4 stages or 5 stages or more stages, the result is also similar. It did not reduce the error. And we also try to reduce the error by a variable deep width for different approximate multiplier. In the first approximate multiplier, A1, 8 bits for the multiplier. The second one, we use 7 bits. The third, we use 6 bits. We reduce the data bit, and we also found that the error did not influence very seriously. It's about 1% error. So the result, we will add them together. This page shows the comparison between our proposed E.am and the relative work. If there are two positive inputs, the results are also the same. If the iteration increase, the error will be decreased. Then if we have one positive input and one negative input, our proposed design will still work correct, but the relative work will be crashed. So we solve this problem. We also realized the relative work and our proposed architecture in 90 nanometer CMOS technology. We found that we can reduce the area and also the power. Okay. Then we also try another design in our work. First, we designed a multiplier with truncate and rounded technology. This means TRAM. It also follows the relative work. The relative work is truncate and rounded based scalable approximate multiplier. TOSAM is from the relative work. In this work, it has the equation is shown as D here. So it applies a positive number n. The n can be replaced by this term multiple f. And for if I want to multiple a and b two positive number, you can replace this term multiple SA and SB. And SA and SB are in the range of 1 and 2. Then you try to replace SA and SB by y. Y is equal to s minus 1. So YA and YB will be in the range of 0 to 1. So the equation can be transferred to here. In this equation, you can find that it has YAT and YBT, and also YAATX and YBATX. YAT and YBT are T-bit truncation of YA and YB. YA approximate and YB approximate are H plus 1 bit approximate term. So in conclusion, it means that in TOSAM, they have two parameters. One is T and one is H, right? I can use different T and different H to have different truncation and different approximation about the multiplier. So let's show the next page. Okay, this is the block diagram of TOSAM. Is that T is equal to 3 and H is equal to 7 in their experiment. And in all proposed TRAM, it is the modified version of the TOSAM. It's a TOSAM with dual mode. I also put the equation here again. Our idea is, in this equation, if Ka and Kb are small, it means that the A and B are small in this case, right? So in this case, we can transfer to a low precision mode because the result will not influence the error will not influence the real result, but it will reduce the precision. So we select T is equal to 0, H is equal to 2. If the Kn and Kb is larger than this value, we will transfer to high precision mode, H mode, and select the same T and H as the related work. With this method, we can find that the error will increase about 0.11%, but the error is reduced to 62%. We can reduce many areas. We also realize our design and compare with the related work. The results show that we can reduce the area and also with the slight increase of the error in this work. Okay, this is the reference about our proposed design. Then I have prepared some time for the QA. If someone has a question, please raise your hand or let me know, okay?
Okay, thank you. Any question? No question? The design of your AI accelerator seems very powerful in different areas, such as signal processing,
Yes.
such as the DRAM design, right?
Right?
Can it be applied well to the optimization design for wireless and mobile communication system, such as the resource and the channel allocation or some parameter optimization?
Yes, in automatic control research area, they will use the deep network to update their parameter by the AI to find the best parameter in their application by iterative to tune by the environment and the agent to find the best result. Yes.
I'm wondering, do you have other examples besides the signal besides the image processing? Because it seems like 2D.
Yes.
I didn't see 3D. Right?
Yes, because in 3D architecture, I focus on the thermal problem, not the AI problem. So I always focus on the AI problem in 2D chip. So I only do some oscillator, but the oscillator itself is still the 2D chip. So we focus on the architecture or algorithm design for the 2D chip. Okay.
I see. No question? This is it's a little early.
Okay.
Okay. If no question, I will remind you the next 2 weeks our seminar class will be online. Okay. Okay, that's all. Thank you.
Okay, thank you.